First, I thank our management and principal for giving this opportunity to organize this TEW in our campus. Next, I welcome our program coordinator and one of the resource person of this workshop, Professor K. N. Raghavan sir from IMSC Chennai. Also, I thank Professor K. N. Raghavan sir for his constant support and guidance. In May 2019, under his guidance and support, we successfully conducted TEW on algebra and multivariable calculus. Thank you, sir, and I welcome you, sir. Also, I thank Professor K. N. Raghavan sir and all NCM members for giving us another opportunity to host TEW 2020 on algebra and discrete mathematics through online during this pandemic situation. We expect your continuous support and guidance in future also. Next, I extend my welcome to all the resource persons, Dr. Anirban sir, Dr. Sangaran Vishwanath sir from IMSC Chennai. Last but not the least, I welcome my department colleagues and all the participants for this online workshop. I welcome you all. Now I request Mrs. Meena Kumari to introduce our today's resource person, Professor K. N. Raghavan sir.
Thank you, Radha ma'am. Now, it's my privilege to introduce our eminent speaker of today's session, Professor K. N. Raghavan sir, IMSC Chennai. He completed his MS degree in IIT Delhi. He completed his PhD degree in Purdue University, USA. He got more than 30 years of teaching experience. His area of specialization is representation theory of groups and algebras, flag varieties, and subet varieties. He published more papers in international journals. He played a role as a coordinator for TEW 2019. With his effort and guidance only, this online TEW 2020 is possible in this meantime. With these few words, I welcome Professor Raghavan sir to deliver his lecture. Welcome, sir.
Thank you. Thank you for that introduction. So let us begin. I welcome the participants to this 6 weeks long TEW. I hope you will find it useful. Please do participate actively so we can all gain the maximum benefit from it. So with these words, let me start. Can I share screen now?
Yes, sir.
So if you could let me share screen, we can start the lecture. I'm still awaiting it. Take your time though. Okay, I hope you can all see the screen.
Yes, sir.
Okay, so the title of my series of lectures, there are 3 resource persons in this TEW, and each resource person is going to conduct a lecture course of 6 lectures and tutorials associated with those lectures. So there are 3 lecture courses, and mine is titled Group Actions and Applications or something like that. It's about group actions. So I just distributed some notes. So let me write out. I think you received this email, but in just in case. Am I not audible?
Yes, audible, sir.
You are
Audible?
audible, sir.
Okay.
You are audible. You are
Okay. So if you go here, this is my web page. Okay, and you will see a link which says for lecture notes and courses, etc. And if you click on that, then you will be taken to a page where on top you will see group actions. There are some notes with Mepco, TEW at Mepco on it. So you will find those notes easily on if you go to my web page. Okay, so why study group actions, or why study groups? I don't know if any of you have any idea. Why should we study groups? Does any one of you want to venture an answer? If so, you can unmute your mic and
to study of the symmetry of the object.
Very good, very good. I would think that's a very good. So it's because of symmetry, right? We want to study symmetry. At the moment, it's a vague term, right? So what is symmetry? So what is symmetry? So why do we want to study groups? Because we've said it's because of symmetry. And I suppose for symmetry itself, no justification is needed, because intuitively, all of us understand that symmetry is something very important. It is, in fact, so let me read out a few lines from the notes that I have. These are the first few lines of the notes. It says the following: symmetry is everywhere around us. I repeat, symmetry is everywhere around us. It underlies beauty and structure. Its study is therefore important. So what we are saying is there is no need to further justify the study of symmetry, because it is there everywhere around us and it underlies beauty and structure. The theory of group actions, which we will be concerned with in this unit, is indeed the study of symmetry. Okay, so we have justified why we study groups or group actions, right? Because it is indeed the study of symmetry. And symmetry itself, it's obvious why we want to study it. There is no need to further justify it. But then now the question arises, what is symmetry? Right? What is symmetry? So we need a mathematical definition of this. Right? Rather than a vague notion, we need a mathematical definition. Okay. Rather than, I'm going to give you later in this today, I'm going to propose a mathematical definition of symmetry. But before that, let us take a motivating example. So I'm going to motivate this study of group actions with the help of this example. So let me So this is a very practical sounding example. So let me tell you what the problem is. Okay, describe. I will not write so much as speak. So imagine that you are a necklace manufacturer. So necklace. We are interested in necklaces. Okay. So for our purpose, what is a necklace? So you let's say you have beads of various colors. Okay, so as a necklace manufacturer, you have access to a large supply of beads of various colors. And let's say for simplicity that these beads are all uniform except for their color. Okay, so you have a bunch of blue beads, you have a bunch of red beads, green beads, white beads, black beads, etc. Now the problem is the following. Suppose I want to manufacture a necklace with, say, 10 beads, right? And say 5 colors, fixed colors. Let's say white, black, blue, or red, let's say yellow and green. Okay, the question is, how many beads can you how many necklaces can you produce? This is the question. Is the question clear? So let us simplify this a little bit. So see, the answer is going to be complicated, as you can imagine, right? Suppose I could choose all beads to be white. That will make it 1. I could choose all beads to be black. Okay, I could choose all beads to be red. I could choose maybe 10 of them to be red, 1 yellow, 1 green, right, etc. So clearly the number is very large. So let us simplify this a little bit. So for the sake of understanding, let us say we have only, so simplify, and let's say we have, let's say even 8 beads and just 2 colors. Let's say white and black, or blue and, okay, I have here access to blue and red. So red, okay, and then there is blue. Okay. Okay. So I have access to a large supply of beads. Okay. I'm supposed to use only 8 beads. They can be either all red or all blue, or some could be red, some could be blue. And the question is, how many necklaces can I make? So let us understand the problem. So what I mean by, for a minute, let me show you just an example of, so for a minute, I'll stop sharing and I'll, so I hope you can see me now. Am I showing on the screen?
Yes, sir. You are on this.
I'm on the screen. Good.
Yes, yes, sir.
Okay. So, so I made, here is a string. I have some red beads and blue beads. And you see here, I have, so that's a necklace with, it doesn't look like much of a necklace, but you should imagine something like this with two beads and 2 blue beads and 2 red beads, right? So, okay, I had the intention to make a video with this, but for lack of time, I didn't manage. So let us just describe it here. So I'm back to sharing the screen. Okay. So let us even simplify it further. I eventually want to answer the question for 8 beads, but let's start with just 1 bead to begin with. Okay. So before we proceed further, let me say once again why I am talking about this problem. There are several reasons. One is that it, as I said, it motivates the study of groups and symmetry, but also because in the way we teach mathematics, we seem to jump into things like, oh, okay, here is the definition of group action. Let G be a group, X be a set, and this group action is a map from G cross X to X, etc., which is all fine. In fact, we are going to do that. But at the end of the day, you study all this for applying it and to various situations, and it is important for us to understand how things are applied. Okay, and usually this is missed when we teach formally in a lecture in a classroom. So I am sort of breaking with this kind of tradition um, in order to and putting this application up front. Okay. Um, there is a second reason. There are multiple reasons. Here is another reason. Although this might look like a toy example, this really a slightly more complicated version of this is really at the heart of many applications of what we are going to study. So it is not just for it's not just for this. It is a serious example. Although we have simplified it, but it is really one which has itself has applications. We will not have time to talk about those, but that doesn't matter. And the third thing is, we also don't seem to understand the importance of experimentation in mathematics, right? So with a problem like this, what you should be able to do is sit down and answer for, understand the problem, grapple with the problem, and without doing such grappling, we are usually not able to understand what the get the hang of the problem, understand what the essence of the problem. Okay, so for all these multiple reasons, I am starting with this motivating example of this necklaces. So understanding this example well and spending time on it will be very good if you want to understand what follows. Okay. Okay. So suppose I have only 1 bead. Okay. Then how many necklaces can I make? So by making a necklace, I mean the following: you take a string, okay, and you what is the word for it? You push it. All these beads come with small holes with through which you can push a string. Okay, so you string the bead. Okay, you string the bead. So let me draw the. So I have a string like this, black strings, and then I string the bead. So I have this bead here, and then I close the string. So I pull out. So these are loose ends of the string, and then I can maybe I have something with which I can burn the 2 ends of the string to make it uniform. Suppose I have some device to make this. So this looks like this is a necklace. So this is a string with only 1 bead strung through it, right? And that bead could be red. Of course, the other option is that bead could be blue, right? So these are the only 2 necklaces that I can make. right, with one bead. There are two colors, blue and red. Therefore, there are only two necklaces. Okay. How about with two beads? Can somebody please answer that question?
3 necklace.
3 necklaces. Very good. Which ones are those, madam? Very good. Can we draw them? I'll draw them as you tell,
Yes, sir.
tell
Both
me.
red.
Both red.
Blue.
Ah.
And one red, one blue.
Very good. Excellent. Okay. So let's do that. So is that clear to everyone? Both red. That necklace looks like that. Both blue. That necklace looks like that. And one red, one blue, right? Very good. So the answer is 3 necklaces. Let's do with 3 beads. So let's start in the, I'm waiting for somebody to answer. So all the beads can be red, right? Let's say 2 of them can be red. Maybe only 1 of them can be red. Can somebody unmute and tell me the answer while I'm doing it? So this is the necklace with all red beads. This is the necklace with 2 red and 1 blue bead. This is the necklace with 2 blue and 1 red bead. This is the necklace with 3 blue beads. So what is the total number of necklaces possible here? 4 necklaces, unless I've made a mistake, right? Do we agree with this, all of us? Or is there a problem? Did I leave out something? Can somebody volunteer, please?
So what about the arrangement? Is there any condition that next color is different color?
No, there is no condition like that. There is no, how many different necklaces can you make? That's the question. So you're free to choose all of them to be red, all of them to be blue, some of them to be red, some of them to be blue, entirely your choice. Is the statement, is the problem statement clear? It is
Yes,
important that we understand the problem correctly. Okay. So is that clear? Was that anomaly?
Yeah, yes, sir, clear.
Okay. Clear. So is the answer okay in this the 3 beads case, 4 necklaces?
Yes.
Yes. Okay. Let's do the 4 beads case. So let me draw some. How can somebody please? It's slowly going to get very interesting. So let's see how many that we can do here. So let me write all 3 red, all 4 red, right? There is one necklace like that. Instead of drawing it, that is one of them, right? Can I say that instead of drawing it? And then 3 red plus 1 blue. How many necklaces can you make with that? 3 red plus 1 blue. There's kind of only one necklace you can make, right? Let's now ask for 2 red plus 2 blue. How many can you make with this?
2.
2. Yeah, and now you see with the same number, I can make now 2 of them, right? Namely, the red beads are next to each other like this.
Red, blue, red, blue. That is blue.
Red, blue, red, blue. Very good. Thank you. They could alternate or they could be together,
Yes.
right? This is one possibility. This is the other possibility, right? So let me draw the string. Sorry, I hope my pictures are not great, but I hope you're able to understand. Okay, and then I have 1 red plus 3 blue, right? Or I have 4 blue. So what is the total number of necklaces? 1, 2, 3, 4, 5, 6.
6.
6 necklaces. Do we agree with this? That there are 6 necklaces possible with 4 beads. Okay, let's try with 5 beads. I want to repeat here that this may seem very boring, but in fact it should not be boring. This should be part of exploration in mathematics. We should, it is, I could of course give you the answer in general. I could lecture and start giving you the answer in general, but I'm afraid that is not going to work very well in terms of understanding. Okay, so in order to understand, we must get our hands dirty. At least the only way I seem to understand any mathematics at all is by first getting my hands dirty and trying to understand a few examples. We do not emphasize examples these days in our teaching, and that is an issue with our teaching, and that's something we need to address as teachers, since all of us are teachers. Okay, let's do with 5 beads. So how many can I do? How many with, there's of course 1 with 5 red, right? There is only 1.
So look like partition of 5. 4 plus 1, 3 plus 2.
Right, that is the top one, but already, for example, this partition 2 plus 2 of 4 gave me 2 necklaces, right? You understand what I'm saying? The partitions will play a role, but we need to, there is a more to the counting. It is not just partitions.
Yes, yes, yes.
Right? Because, for example, here 2 red and 2 blue, there are 2 necklaces. This is just one partition of 4, but there are 2 necklaces. Right? And as the numbers increase, suppose I have 10 beads and 6 blue and 4 red, then these 4 red beads can be within those 6 blue beads in different arrangements, right? So the numbers are going to get larger and larger. Okay, so 5 red, there is only 1, and then 4 red and 1 blue. How many will there be?
There are 4, I think.
4. Why 4?
Alternately, we can fix that blue.
2.
Okay.
What do you
2.
mean alternately we can fix that?
2.
Why 2?
So all the 4 in the middle of 4 reds, you can fix 1 blue.
Yeah. So let us draw this. Good
Yes.
question. Let's understand this. It's this important to understand. So
So only one, sir.
Only 1.
Because you have to
So
join
let's
the
see.
agent.
So this is a necklace, right? with 4 red and 1 blue. Right? Can I do anything else? Okay, maybe you're thinking, so let's draw this. Maybe you're thinking I can put the blue here, right? Okay, let's understand. Is this a different necklace or the same necklace?
Same one. Actually, this is symmetry.
Same
of-
only.
Same only, right?
Same.
That's why I'm thinking of them as not as pictures, but as necklaces. So if I just turn the first necklace around, I'll get the second necklace, right?
Yes, sir.
Correct? So how many can I make with 4 red and 1 blue?
Only one.
Only one.
Only
Exactly.
one.
Only one. So with 5 red, there is only one. With 4 red and one blue, there is only one, right? Okay. So what are my other options? 4 red, 3 red, and 3 blue.
3 red, 2 blue.
Sorry. Thank you. 3 red and 2 blue. Thank you. Okay. How many can I do?
Again, ma'am.
2, sir.
Let's see. So the question, the
Yes, sir.
thing, 3 red and 2 blue.
Again, 1.
Okay. Let's see.
So alternative blue one and then
The blues
Blue, red,
together,
blue.
Blues together was 1.
There should be two.
Blue separated is 1, right?
yes.
Have we counted them all? Are these all, meaning with 3 red and 2 blue? Are there any other possibilities?
In between red, sir.
Yeah, but if you do in between, so can you find some arrangement that is different from this and this? Or will any arrangement be one of these?
Only 2, sir.
Only 2, right? So what is the number of necklaces? Okay, so now let's get a little faster in our calculation. If I take 3 red and 2 blue, how many will I get? Another 2, right? Sorry, 3 blue and 2 red will also
Another
give
2.
me another 2.
Two.
So
Yes.
that will be another 2, and then
And
4.
1 red, 4 blue, that is another one.
Yeah,
And all are blue.
very good. So
Yes.
total number is
Totally 8.
very good. 8
Yes.
necklaces. Right? So I'm not writing it down now, but you understand that you can complete the calculation, right? By, whether now see, I'm using some symmetry here. Namely, I can switch blue and red. That is a symmetry, right? See, we are using symmetry now we are exploiting symmetry, although it sounds rather trivial, but it is an important observation. So if I choose 3 red and 2 blue and try to make necklaces, the number of necklaces that I get will be the same as if I choose 3 blue and 2 red, right? Because whether I use red or blue, the same calculation I'll do with red replaced by blue and blue replaced with red, right? So there is a symmetry between blue and red. So that's a symmetry. There is a symmetry even here. Okay. Okay. So with 5 beads, there are 8 necklaces, right? Do we all agree with that?
Yes, sir.
Okay. So, and so on. 6 beads. Let's do 6 beads. So how many here? Let me now make it 6 blue, 6 red, right? How many of them? 1, right? 5 red plus 1 blue. How many?
1.
5 red plus 1 blue, 1. Very good. Okay. 4 red plus 2 blue.
2.
Okay, the answer 2. How many of you agree it's 2 and how many of you So how can the two blues be distributed? So maybe the blues are all together, right? Something like this, right? Okay. Maybe the blue is okay. That's maybe the blues are separated. Okay. Maybe like this. Are there anything else possible? Is there anything else that's possible?
Yeah, possible.
Possible. So now you see it's not so easy because
Yes, yes.
you can have this blue and these two red next to the blue and then a blue here, right? And then these two are red.
3 red.
3 red, right, exactly. So 3 red. So between the two blues, there could be 4 and 0 or 2 and 2 or 3 and 1, etc. Right? Okay. So you see it's already getting complicated. And then for, is there anything else possible or is this it?
That's it.
That's it. Okay. Anybody, do all of us agree?
Yes, sir.
Okay. So for
Yes,
this,
yes.
3. Okay. And how about now 3 red and 3 blue?
Three choices.
Well, let's see. How are you so sure?
All together blue and red.
Okay, all together blue
And
and
all
red.
together red. Then blue, red alternate.
Blue, red alternate. Okay.
And two blue, two red, two blue.
Blue,
No,
red
no.
alternate.
Yes. Okay.
Okay.
Yes.
Sorry, my necklaces are getting very small, but
Yes, sir.
okay. And anything else?
Two blue,
Yeah. So
1
4
red.
red. 4 red.
maybe 2 red and then 1 blue like this and 1 red like this. And then the 2 blues together. Sorry, I'm making a mistake here. Okay. Is this one of them? So these 3 are distinct, right?
Yes.
Okay. Any more?
That's it.
No.
That's it. Okay.
No.
All of us agree, or do any of us have another suggestion?
Only 3.
Only 3. Okay. I also agree. So let's say only 3. Okay.
Okay, sir.
Okay. By the way, I could be making a mistake. I don't remember the number. Okay. So there is just make sure that we have not forgotten any of these. These 3 are clearly different, right? Because here 3 blue are together. Here they are alternating. Here there is 2 blue together and 1 is separated, right? Okay. I also agree that. So what is the total number of necklaces here with 6 beads?
13.
Let's see. 3. So on the other side, there will be 3 plus 1 plus 1 again,
Yes,
right?
yes.
5
Yes.
plus, so very good. So 3 plus 2 is 5, 5 plus 5 is 10, and then this 3, 13. Very good. I also agree. Okay. So you get the hang of it, right? What to do. Right? So I want you to work out as homework for 7 necklaces 7 beads. 7 beads and 8 beads. See, do not think that this is some, do not try. If you try to, you can try to guess the answer. You will need to be, I think, a genius to guess the answer, because it is not a pattern that there is some pattern. Of course, there is a pattern, but that pattern is not at all obvious what it is. Okay. So, so it's good for us to just enumerate and see, but also be aware that very soon the problem will get out of hand. Okay. So, meaning for 10 beads or 12 beads, you will not be able to enumerate within any reasonable time, right? For 6 beads, we did it within, say, 5 minutes or maybe 10 minutes. But with 7 beads or 8 beads, even with 8 beads, it will take a long time. Okay. But what I want to do now is, I mean, other than encourage you to try and do this at home, you should do this at home. You will probably spend an hour or two trying to do it for 7 beads and 8 beads. But let me assure you that that time spent will be worth it. Okay. Okay. So let's now try to understand some features of this. So I'm going to use 8 beads as my illustrating example. Okay. So now we are going to think about how to how to go about counting necklaces with 8 beads, right? We are going to now start thinking about it, use the symmetry available, etc. Okay. So should we proceed there? So far, is everything clear?
Yes, sir.
Okay, good. So let's proceed. Okay. Maybe I'll go to the next page. Okay. Okay, top of the page. Let's see. So beads, so necklaces with 8 beads. Okay. So let us understand. Say each necklace I'm depicting by a diagram, right? So here is what I mean by diagram. So I think of, there are 8 beads. So I draw these 8. Imagine an octagon, right? So there is okay, let me draw this. This is a circle. That's the string. And I mark out these positions on the string. So let me mark these positions in this color. Right? And in each of these positions, so there are 8 positions marked. Right? So how many, and in each position, I can place a bead. And that bead can be either red bead or a blue bead. Right? So for example, I can place a red bead here, 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 and blue beads here. So let's do an example. Okay, let me just do an example which I want to, which is there in the notes. So you can, because I want to illustrate a certain point. So So let me, so here it's red, 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 and the rest are blue. Okay, so that's it. So this is a diagram, and we can think of it as a necklace. Okay, let me draw one more diagram. Sorry, my circles are not really circles. So this has, okay. Okay, so these are two different diagrams, right? By diagram, I mean just a picture like this with reds and blues placed in those marked positions. Right? Now, these two pictures, as pictures, they are different. But as necklaces, are they the same or they are different? So this is imagine this to be a necklace and imagine this to be a necklace.
Same only.
Same only, right?
Yes.
Same necklace, correct. So these diagrams are different, but as necklaces, they are the same. Is this point very clear?
Yes, sir.
Very good. Okay, so let us draw. I want to draw two more pictures here and ask you to, they will be different as diagrams. And I'm going to ask you if they're same or different as necklaces. Okay. How are is this a different necklace or the same necklace from the, so we have said these first two are the same, right? So you can say the first, to go from the first to the second, what I do is,
It is same only. Again, it is same.
it is the same only. So how do I see that this third one is the same as the
So
as the
continuous
second
3
one?
blue, continuous 3 blue, then continuous red. The
Third
same
one
picture is
different
repeating.
No, but don't answer me like that. You have to tell me how
Just you are rotating this.
you are rotating this necklace. If I rotate this necklace, will I get this necklace?
No, it's reflection.
No, no, no.
Ah, okay. So what exactly should I do to this necklace to get here?
So either reflection or rotation or inversion.
Flipping.
Flipping, yes. Okay. You flipping, which is the same thing as saying deflect. So let's do the following. Let's understand how to go from this necklace to this necklace. Okay. So what I'm doing is, maybe I'm reflecting here, right? Then what will happen? I will get, meaning that is the same thing as if I reflect here, that means I'm flipping the necklace like a dosa, right? You understand what I'm doing?
Yes.
Okay, so I'm flipping the second necklace like a dosa. Imagine putting some ladle or what is that, whatever it's called, a flat surface beneath the dosa and flipping it, right? So if I flip it, then the three red beads will go to this side, and this red bead will go here, and the blues will now change places, right? This will be there, this will be here, and these two will go here. Okay, now this will look like this. Okay, and then what is the difference? So from how do I go from here to here now? I can rotate this, right? If I rotate this, so I can rotate this and go here. Is that clear? So this is a flip. From here to here is a reflection or a flip. From here to here, there is a rotation. From here to here, there is a rotation. So already there is this time. Okay, this may right here rotation. Is that clear? So to go from the second to the third, what I need to do is flip it and then rotate it. Is that
Yes.
right? Maybe there are other ways in which I can get there as well, but that is definitely one way of getting there, right? You flip, rotate, flip, and then rotate, right? Maybe there are other ways. You want to think whether there are other ways of doing this, getting from here to here. Anybody wants to suggest it's a direct way of going from here to here?
Not possible, I think.
Not possible?
Yeah.
So what can we do? Let's try. Do you have a proof that it's not possible?
So we have only two possibilities, either rotation or flip.
But there are many. Okay, rotation you cannot do. Okay, but you may have to flip. So how many flips can you do? How many different flips are there? These positions have to go.
We are doing the diagonal.
Yeah. So you can do this flip and then we go here, right? Or we can do along this. If I do this, then will I get this? No.
Yeah.
Right?
By
Yeah.
interchanging the colors and then rotate.
You are not allowed to interchange the colors. You're not allowed to interchange the colors. See, in a necklace, you cannot do that magic, right? With a necklace, you can flip it, you can rotate it. But you don't have, see, you understand what I'm saying. That's why I'm using the word necklace. It's a good thought, but I hope you understand what I'm trying to say. Is this clear?
Yes, sir. Yes, sir.
Okay. So what other options are there for me? So there is this diagonal, there is this diagonal, right? I'm not drawing this very well. So with this circle.
So you can use the circle diagram in the option, sir. In the math tech, you can see the option math tech in the nearby. You can see the rectangle, a square. You can click that one.
Which one? Sorry.
Math tech, I think so. Math tech. Near to the you can click that arrow.
Oh, this one?
Square. No, sir.
Square one. Okay.
Yeah. No, sir.
No, sir. Previous one.
The math tech. Yeah. That one. You can click that. You can see the
draw
circle. Draw the circle.
Okay, very good. Thank you, Anamali.
Thank you.
So, okay. So that's a circle. Okay. So, draw line. Okay. Draw line. Okay. So here is one line. So let's draw the. So okay, those are the 8 positions, right? And I have these diagonals, right? Right? And what else? So there are, how many reflections are there? Are there other reflections? How many rotations are there? How do I get back to this?
You can click that pens.
I can click that pen. Okay, I've clicked it. Okay. Oh, it's still thinking that I'm drawing lines.
Yeah, you can click again on the top. Yeah, on the picture you got to click this.
On the picture I have to click?
No, in that arrow, the option you got to click that.
What?
Near one. The picture, yeah, click that one.
Click that one. Okay.
Yeah. Again you can click. Is
again I can click.
Yeah.
Okay. Thank you. Sorry for. Thank you for the educating me. Thank you. Okay. So how many rotations are there?
8 rotation.
Very good. 8 rotations. 8 rotations. How many reflections are there?
8 reflections.
4.
8. 4. Okay. Let's see. I hear 2 answers. These lines that are drawn here, how many lines are there?
4 lines.
There are 4 lines, right? And therefore these give 4 reflections. But are there more reflections, or these are all the reflections?
Only 4, sir.
Yes, only 4.
Are you sure? See, what I can try to do is the following. I can draw, there is this line. And then it will go, see, if I draw this line, for example, I have drawn like this, then these 2 will be fixed and these 2 will interchange places, right? But when I draw this line, there is all 4 pairs. There will be 4 pairs, and each pair will interchange places. So, do you agree that I can also reflect in the lines? There are 2 kinds of lines.
Yes.
One is passing through these points. The
Another
other
one is midpoint of the line.
Midpoints of the line.
Yes.
So let me draw them now. Let me use this. What is this called? Math. So is that the right? No, this one, right?
No, sir. Yet next one, map check. Yeah.
Yeah. Okay. So draw line. Okay. So let me draw now. Oh, that's not good. That picture is not very great, but so these are 4 more reflections. So I need to click on this again. Okay. These are 4 reflections. So how many possible actions do I have? I have 8 reflections plus 8 rotations.
16.
So let us see if I can go from one to the other by any of these means. So from the second to the third, so suppose I reflect, is there some reflection that I can do? So for example, if I reflect along this, then will I get here? These 2 will get interchanged, right? This will go where? This red will go?
Yeah, you will get
here.
that one.
Right? So you can go from here to here by means of this reflection. Correct? Do you agree? Maybe you're not seeing it because my picture is not very good. But let us, so let me draw this thing here again. This line here again. Okay. Now you see, when I reflect, what will happen? These 2 will get interchanged, right? And those are red. These 2 will get interchanged. Very good. That is red and this is blue, right? These 2 will get interchanged. Well, that is blue and this is red, which is as it should be. And these 2 will get interchanged and they are both blue. So do you agree that when I go from, I can go from here to here by this flip?
Yes.
Yes?
Sir. Yes,
okay.
sir.
Very good. So So sort of we know the now all possible symmetries, right? So there are 16 symmetries of these diagrams. By symmetries, I mean I can take a picture, right, and perform any of these 16 operations. I can keep rotating it, or I can keep reflecting it. So is the statement clear?
Yes.
Yes. And the answer to how many necklaces are there. So let us say the following, that so what do we have? So I want to introduce now, take the set of all diagrams. So now I want to mathematically formulate how to solve this problem. Right. Consider the set of all diagrams as above. By a diagram, I mean a picture like the above. How many possible pictures are there? There are 8 positions. And in each position, I can place either a red bead or a blue bead. I'm not asking if they're different as necklaces. For example, these two are the same necklace, but they are different as diagrams. So first, let me just count the diagrams. How many diagrams will be there?
$16.
Why? What is your logic for 16?
So there are 8 reflection and 8 rotations.
No, don't. So diagrams, we don't need all that. The diagrams is, see, this is a different diagram. This is a different diagram. So in the diagrams, I am not, okay, let me explain what I mean by a diagram. A diagram is just a picture like this, where at each position, I choose either a red or a blue.
There are 2 choices for each position.
And how many positions are there?
8 positions.
So the answer is, yes, you said it
2
correctly.
power 8.
2 power 8.
8.
Yes.
Okay. Yeah.
So there are 2 power 8 positions, diagrams.
8 position.
There are 8 positions, right? And at each position, the bead that you place can either be blue or can be red. So there are 2 choices for every position. So there are 2 ways I can choose that position, right? I can either make it red or make it blue. So using elementary permutations and that you have learned in school, you have eight different things to do. Namely, you have to choose for all those positions either a blue or a red, and these are independent, right? I can put blue here, then the next one red or blue. It doesn't matter what I've done earlier. So these are independent, and each has 2 choices. So it is 2 times 2 times 2 times 2, 8 times. So that is 2 power 8. Is this clear?
Yes, sir.
Yes, sir.
Okay, good. Now on this, let me introduce an equivalence relation. So on the set of diagrams, introduce an equivalence relation. And that is 2 diagrams, say D1, diagram 1 is equivalent to diagram 2 if D1 can be obtained from D2 by one of the 16 symmetries above. So by these 16 symmetries, I mean 8 rotations plus 8 reflections. Okay. So there is something here to be, so intuitively this seems clear, but there are, if you try to prove this formally, there are a few things you need to check. So let's see. I am claiming this is an equivalence relation. So what all do I have to check? Is every diagram equivalent to itself, related to itself?
Yes, sir.
Yes. I don't need to do anything. I just take the identity symmetry, because one of these 8 rotations is the identity rotation, right? Meaning, identity rotation, meaning I don't rotate at all. I just stay where I am, correct? That's like the identity element of the group, if you wish. I'm going to talk about the group that is underlying in a minute. Okay.
So one of these symmetries are a combination of these symmetries.
Ah, good question. There you are. Very good, very good. So you see here, see, Annamalai is asking a very nice question. He's asking, see, do I, of course, I can flip and then rotate, right? That is also that. Then if I flip, then it will be the same. The necklace will still be the same. And then if I rotate, it will also be the same, correct? So he's asking a very good question. I can, if I say, if D1 can be obtained from D2 by a sequence of one of these 16 symmetries. That's what you're suggesting, Annamalai, correct?
Yes, yes, sir.
Rather than I'm jumping the gun and saying one of these 16 symmetries. Right? But here is the solution to the problem. See, as you saw here, we went from here to here by means of a reflection and then a rotation, right? In the first case, right? When we originally said, when we went from picture 2 to picture 3, right? I hope you're able to see my arrow. Then we went by a reflection and then a rotation, correct?
Yes.
But then we also saw we could go directly by this flip,
yes,
by reflection along this. So the claim now is these 16 symmetries form a group. In other words, if you do one after another, it will be one other element of that symmetry.
Yes.
Okay?
Yes, sir.
Okay. So I am not proving this, but take this for granted. So that's a very good question, Annamalai, you're asking, and I hope I have answered your question.
Yes, yes.
Okay? Okay, good. So the thing that we are not proving, but we are claiming is, I repeat, if I do a sequence of these operations, like I flip, then rotate, then flip, then rotate, you can do it 100 times, right? You can choose one diagonal and then flip, and then choose another diagonal, flip, and then do a rotation by whatever, one of these 8 rotations you can do. And then you can flip by some other where, and then do a rotation. Whatever you do, it will be one of these. That is the claim. Okay. So in other words, these symmetries, the symmetries, so let me write it, these 16 symmetries form a group. Okay. In fact, it is the group you might have.
It's a dihedral group.
Dihedral group. I don't know whether you denote it D8 or D16. What is the
8?
D8. Okay. So what you call, it's the group D8. Okay. So what is this group? This group consists of the symmetries of this octagon. That's what we say, right? Dihedral group D4, we say, is the symmetries of the square. Now this D8 is the symmetries of this octagon. Okay. And so now let's come back to proving, try to prove that this is an equivalence relation. So why is this an equivalence relation? If D1 is related to D2, then why is D2 related to D1?
Reverse process. You can do.
Reverse process. Because it's a group, the reverse process, right? If I rotate by 45 degrees in the clockwise direction, I can rotate by 45 degrees in the anti-clockwise direction. Or what is the same, I can divide by 360 minus 45, that is 325, I guess, or 315. 315 degrees. If I rotate by 45 first, and then by 315 degree next, it will come back to the original position, right? So if I do a process, one of these symmetries, its inverse is also there. Okay, so that shows that this is if D1 is related to D2, then D2 is related to D1. And how about if D1 is related transitiveness or transitivity? D1 is related to D2 and D2 is related to D3, then is D1 related to D3? Well, we just said that if I do two of these operations in succession, one after the other, that is equivalent to doing one of these operations, right? Like in this example above, right? Where we did two operations to go from here to here, right? Reflection and then rotate. But that is the same as
Midpoint reflection.
Yes, reflection in
Sides
this orange
midpoint
line.
reflection. Yes.
Right. Okay. So do we agree that this is an equivalence relation?
Yes, sir.
Okay. And now what are we asking? We are asking how many equivalence relations are there, right? That is the question. Because each equivalence relation represents a necklace. Correct? Because if two of these diagrams represent the same necklace, means what?
It comes under one
I
class.
can flip it or do something to it and get the other one, right? So I am claiming, here is the upshot, final. This is our observation today, our final observation for today. And that is that the number of necklaces equals number of equivalence classes. Is this, have I convinced you that this is correct? This is reasonable to expect?
Yes.
Because
Yes,
I repeat, because you see, after all, how do we represent a necklace? By means of a diagram, right? But we understand that two different diagrams can represent the same necklace. When do they represent the same necklace? If and only if I can either do a flip or a rotation or a combination of these. Doing a combination, as we have observed, is the same thing as doing one of these operations, right? So, so for example, from here to here, these are two different diagrams, but they represent the same necklace because they are in the same equivalence class, right? Because I can go from one to the other by means of one of these operations, namely in the case of from 1 to 2 by means of a rotation. So is this okay? I will wait for questions from you because this is an important point. So if there are questions, this is a good point to pause and ask for questions. So if you have any doubts, please do. You can ask anytime, of course, but especially during these pauses, I will explicitly pause and ask for questions. Is what I'm saying, are you convinced with what I'm saying?
There's a number of different necklaces or number
of different necklaces, of course. Number of different necklaces, right. Number of different necklaces. Of course, that's understood. Yes, correct. I meant that, didn't write it because that's understood. Yeah. Any other questions, or is it okay? Okay, I'll proceed, but you can ask me questions anytime. So what is the point? So let me now relate this to what we are going to do, right? So I said this is a motivating problem. So towards the middle of our course, we will actually solve this problem, right? Not just for 8 necklaces, but we will outline a method to do any number of necklaces, right? Any number of beads with any number. So, sorry, I said it incorrectly. Let me repeat. Not just for necklaces with 8 beads, but counting necklaces with any number of beads, with 10 beads or 15 beads or 20 beads or 100 beads even, we will be able to find a method for counting them by using this process. So now let me tell you how.
So this is only for 2 colors or any
This
color?
is only for 2 colors. Of course, you can now proceed and do it for any number of colors also. Okay?
The observation will correct, sir.
Pardon me?
For any number of colors also, the observation is correct.
The observation is correct. Yes. The
For
observation is correct. Because so, but the only difference will be this. This will not be 2 to the 8 diagrams.
Okay.
Based on the color, it will change. Yes.
This
Yes.
number will change, but
Yes.
none of these, the rest of this will not change.
Okay.
Very good. Very good. That's an important observation. Only this will change. If there are 3 colors, it will be 3 to the 8 diagrams. If there are 4 colors, it will be 4 to the 8 diagrams. But still, this principle is the same, right? Because if 2 diagrams represent the same necklace, means precisely that I can go from this diagram to that diagram by applying one of these symmetries. Is that clear?
Yes, sir.
Okay, good. Okay, so let me now tell you how this is going to be related to what we are going to study. So we are going to talk about group actions, right? So group actions. So what we will do is this, we will take the set, let X be the set of all diagrams. Right? So 2 to the 8 in case of 2 colors. By that I mean if you are allowed to choose beads only of 2 colors. Okay? And then this group D8, this group D8, this is a group. Right? This will act on X. We will make this precise. We will give a formal definition, but intuitively now it is clear what I'm saying, right? So how does it act on X? Given an element of X, which means given a diagram and given a group element, I can perform that action defined by that group element on this diagram. For example, if I rotate this first picture by 45 degrees, then in the anti-clockwise direction, then this blue that you see here, I hope you can see my cursor, will go this here, right? And this this bead will move here, this bead will move here, this bead will move here. So this will become, so if I, so that is the 45-degree rotation. So it is clear, see, even the language is clear. So given a group element, it will act on this diagram, right? And we will, this equivalence class, this equivalence relation will turn out to be, or let me say, sorry, let me say the above equivalence relation. The above equivalence relation will be the what we call orbit equivalence relation. we will define an equivalence relation in general. And it's called the orbit equivalence relation. And this above equivalence relation is just the orbit equivalence relation in this special case. Okay. And then we'll have a lemma. So one of our main lemmas, this is a old lemma. It's usually called Burnside's lemma. But that nomenclature is a misnomer. It is due to actually Cauchy. And and so it was known much before Burnside. It's sometimes called the Cauchy-Frobenius-Burnside lemma. So Burnside was in the beginning of the 20th century, late 19th century. Cauchy was earlier part of the 19th century. So it's also called the Cauchy-Frobenius-Burnside lemma. What it does is it gives you an orbit counting formula. It will tell you how to count orbits. And if we apply that to this situation, each orbit, by an orbit, I mean the orbit equivalence class, right? How many different classes are there? So counting the number of equivalence classes in the orbit equivalence relation. So each class is called an orbit. So we will be able to do that. So if we apply that to this situation, I will be counting the number of equivalence classes, but that is the number of necklaces. So that's how we are going to try and solve this. But I hope you find this interesting because you see, you're exploiting the symmetry here. Right, and so this is how we will, in the end, we will end up solving this problem. Okay, again, let me stop here, pause here, and ask you if there are any questions. So this is where we are going to go. So for the, okay, so let me give you some, tell you about how we are going to, how my lecture course is going to run. So I will I will send you problem sheets from time to time. In fact, sometime today or tomorrow, or maybe day after tomorrow, in a couple of days, I'll send you the first problem sheet. I've already given you the link to the notes, and I will be following the notes more or less linearly. Of course, it's not possible for us to be doing it line by line, but I mean, it is, I hope it is, you can read it. I mean, it is not written, there is a lot of text and it is meant to be read. So I hope you will read it by yourself. I expect you to read it by yourself. And there are problems interspersed in the text. So you can try to do those problems, do those examples. And if you have any questions, we can discuss here. And I'll be covering the main ideas in the lectures, but I repeat, I won't be able to do everything that is in the notes. So I hope you will use the notes, read the notes, and then if there is something there that you want to discuss, if you something that is not clear, of course we will, whatever it is, we'll be happy to discuss it here. Okay. I will, during the class by myself, I may skip over certain things that are in the notes. Okay. So let's go on to now. Let me finish with, or let me ask Guruswami. Professor Guruswami, is there any? Do we have time still, or am I out of time?
So we have 5 more minutes.
5 more minutes. Good. Thank you. You can tell me when I have run out of time, and I'll stop. Right?
Okay, sir.
Okay. Yeah. So let us give the formal definition of a group action, right? So let's. Okay. So G is a group, and X is a set. We say G acts on X, and sometimes write like this: G acts on X, right? People sometimes don't want to write all these English words, so they just write G acts on X like this, denote it like this. Means the following. So G cross X to X, there is a map. Okay. And this is usually denoted, I mean, you can choose a symbol for it, say rho. Then G comma X goes to row of G comma X. Of course, that's what it means to say it. So, but it is better to write this just as GX, right? It looks like I'm doing G times X, but of course, that doesn't make sense because times doesn't make sense. So this map, so this is just notation. G times X or GX just means the image of this G comma X under this row. That's what it means. And this must satisfy the following conditions. So there are 2 axioms, and those are: if I act H on X and then G, this must be the same as GH, like this. So here GH means multiplication in the group. So this is for all G and H in X, in G and X in X. And second condition is 1 times X is equal to X. Okay, where 1 is the identity element of the group. If you don't like 1, you can use E. If you prefer that, that's just a matter of notation. Okay, is this clear? This definition?
Yes, sir.
Okay, good. So let's do an example. So the example that will be relevant to us, for example, for the necklace problem, will be G is equal to D8, right? And X is equal to the set of diagrams. As above. And what is G times X? I have to define G times X is act G on the diagram X. So G will tell you it's either a rotation or a flip or one of those. So what does it mean to, what is this defined as? It is acting that G on the diagram X. Is this clear? And then I claim it satisfies these 2 properties. Okay. So those 2 properties are, if I do H first and then G, right? Then it is the same as multiplying G and H and then doing it. For example, here, let's go back to our case here. Here, this reflection is one group element. Sorry, this reflection or flip in this line is one group element. And then there is a rotation between this and this, right? So, sorry. Yeah, and then there is a rotation here. This rotation is whatever it is, how many 1, 2, 3. So I must come here. So it's 135 degree rotation, right? Because from here, I come down here. So this is rotation is 135 degrees anti-clockwise. So if I do first this reflection, so this diagram, that is my X. This element is H. This element is G. So first, if I take X and then apply H, which means I apply this reflection and come here, and then I apply G, that is the same thing as GH applied to X, where GH is what? GH is the reflection in this line.
Midpoint.
Yeah, in this line. This GH will be the reflection in this line. Okay, so, and if I apply identity, I'll get identity, right? I'm not going to do anything. So these axioms are sort of by definition satisfied. So this will be the example that will be relevant to the necklace problem. Okay, but in general, so next time when we meet, we will talk about symmetry. And I told you we have an intuitive notion of symmetry, but we will try to give a mathematical definition of it. Okay, this is discussed in the notes, so you may want to read it before we meet next time, which is next week sometime, Thursday or Saturday. I don't remember the exact schedule when my next lecture is, but it is clear 7 days away. So you have time enough, and I hope you will be able to read the notes. I encourage you to read the notes, but by some reason, if you are very busy, you're doing something else, and you're not able to read it, then it's okay. We can still. It's not a requirement, but it will definitely help if you read the notes before coming to class. I think I am out of time now, and it's a good time to stop. So let me stop here and ask if you have any questions. You are most welcome to ask. And please, asking questions and trying to get your doubts answered is a very important part of this program. So please do interact, and please do actively participate. For that will be good for that. That way we will all get the maximum out of this program. Okay, I will stop sharing now and ask you for questions. I will, for what it is worth, I will share these notes, right? These 3 pages of notes also with you. Okay. Hello.
Sir? Hello, sir.
Yes, if there are any questions, so let me see the chat box. There are some 10 chats there. 14 necklaces for 7. I don't know. Somebody asked, why can't we use circular permutations? So I don't understand what that means. Okay, so here are some chat questions. I can't see the chat while I'm presenting. So let's see if there are any. Yeah, somebody has posted the notes on the chat, which is good. Thank you so much. Can we generalize these formulas? What does that mean? That question is asked by Saikat Maiti. So anyway, as I have mentioned, I don't know if there is a formula that you can write down for the number of necklaces, let's say with beads of 2 colors. How many necklaces are there? 8 for 8 beads, for n beads. What is the, you can't, but definitely we will be able to understand by means, like we have explained, by means of this orbit counting formula, how that will work. So if you want to expand on this, please do ask the question again. I hope I have answered that. And somebody is asking 14 necklaces for 7. I don't remember the number. Maybe we can discuss it next time and we can see if there are 14 or more, right? Maybe somebody else will work it out. And why can't we use circular permutations? Well, I don't know what that means. If you can explain that, we can try to discuss that. Either now or next time. Either way, I'm open to it. Okay, I guess it has been a long day. 1.5 hours is a long time. So I guess you're tired. It's a weekday, Thursday, I guess. So should we call it a day then?
Yes, sir.
Yes.
Yeah,
Yes.
if you have any questions, however, I'm happy to answer. I'm happy to stick around and answer, but if there are no questions, then maybe we can call it a day.
Okay, sir. Thank you for your wonderful lecture, sir.
Thank you. So we
Thank you,
finished today, and
Okay, sir.
I guess the next lecture is on Saturday
Coming Saturday. Yes, sir. Coming Saturday.
at 5:30.
5:30
Same
p.m.
time?
to 7 p.m. Yes.
Very good.
The same
Very
time.
good. Same time. Okay, and it is Professor Vishwanath will lecture.
Yes, sir.
Yes,
Very
sir.
good. Very good.
Okay, sir.
So, okay, see you then. Yeah, keep safe
Okay,
and
sir.
see you on Saturday. Bye.
Okay, sir. Thank you, sir. Thank you very much.
Welcome. Bye. I'm going to leave. Bye.
Okay, sir.
Bye. Thank you.